because they are further away and they interact better. Okay. Okay, let's thank Christian once again. So next presenter is Austin Breuer, and he will continue presentations based on the same approach, same methodology, but he will apply it to different type of chemical systems.
All right, yeah, I'm Austin. You know, I have a good background, water, we're all chemists, apparently that's important to us, so you know, I'm pretty theatrical in this, but I really focused on the effects of initial momentum in the system that Christian was dealing with. And Christian looked at a lot of that through space, as well as the bonds, and I specifically focused mainly on the bonds. I'm looking at a manganese semiconductor for quantum dots on that level. So I'll walk through quickly what we found out. So just quick background on quantum dots and why this is actually interesting research. Quantum dots are essentially semiconductors that are used to initiate different transitions in the phase of, you know, what's actually being emitted by something that is emitting light. So this has really big implications in nanotechnology, different kind of photovoltaics, as we've seen in solar cells and everything like that. But that's just a quick background on them. And Christian also had a great background on what Marcus theory actually is. The only things I wanted to point out was the actual equation set up by Marcus. And what that includes is a lot of different variables. But the variable that I'm interested in most is really that energy barrier, that energy gap, and what's going to create the ideal situation for any kind of semiconductor, in this case, our manganese one. So the hypothesis of my research and what I focus my research on is, again, finding that optimal kind of initial momentum where we're going to see as much electron transfer as we possibly can. And I'll get into the details of that once we actually come to the data with it as well. So just to first of all see what these look like here. I can play both at the same time. It'd be awesome. So two optimal ones that I like to show for comparison is starting at an initial momentum of 35 atomic units and then also 100 atomic units. As you can see, the 35 atomic units is having trouble actually crossing this barrier and actually transferring electrons over to this manganese acceptor. Now, the one at 100 atomic units is having no problem actually crossing this barrier. So electrons are being transferred between this manganese and bromine bond that's in this complex that was on the previous page. And sorry, I can explain that later if you have any questions on it. What this means really is that as we kind of see this trend continue on, and as we see it with some data here, I'll come back to that slide actually, but with the computational data, as we increase momentum, we're seeing a trend with all of these different outcomes. So the first outcome of kinetic energy is obviously we're seeing more kinetic energy in this bond system, and with that we're seeing more electron transfer. So as you can see, and I'll conclude too, that the optimal range here we're seeing is about between 65 and 100 initial momentum, where we're getting the most of our electron transfer in that semiconductor system. What we're seeing too is as we increase the initial momentum too, we're seeing a higher rate of reaction or those electron transfers actually occurring. So this is just some visualized data. It's again with that the same time period, or I'm sorry, the same initial momentums as before. We're seeing in the first one, there's no electron transfer that's really occurring. There is some, but it's just back and forth. And then this last one down here, there's this back and forth that's continuously occurring, and we see the optimal kind of points that it's getting to. The rest kind of is what Christian already talked about. We're seeing not as much shift in the reaction coordinate or electron transfer, and yeah, those kind of go along with the trends that I already talked about. So in conclusion, what the research kind of showed is that there was kind of an ideal initial momentum between 65 and 100 atomic units. There's definitely a non-ideal initial momentum, which is interesting as well, ones that obviously don't make electron transfer shifts. And just focusing on what the future of the research can bring, looking at changes out of space with this example, or even through things like temperature change and everything like that would be something to pursue in the future.
Okay, let's thank Austin.